Okay, good morning, people. We'll have to move ahead with the other aspects of evaporation, condensation, and what are the other conditions that all this is dependent on. So let me just share the PPT that we were doing last time. You'll see that in this case, we can see the various types of precipitation in the form of rain, snow, sleet, and glaze as such, and how the conditions at the base or through the section of the atmosphere, how the temperatures at different levels tend to change these weather conditions and process conditions as such. Let us move ahead and go into this aspect as such as to the rate at which temperatures tend to fall when we are speaking about different conditions. Okay, and these are called as lapse rates as such. Now, going into lapse rates, let me bring you to this particular slide as such. The uh, adiabatic lapse rate is basically no gain or no loss of heat. And in this whole process, there are various terms. Okay, you'll see that the normal lapse rate, okay, or the adiabatic lapse rate is 6.5 degrees centigrade per kilometer. That means with a height of every 1 kilometer, there is going to be a fall of 6.5 degrees centigrade. Now, as I said, the normal lapse rate is basically uh, a generalization. A generalization. When the natural conditions of air are stable, okay, in the sense that if I'm going to add water vapor into the normal air packet, the conditions could be different. If I'm going to extract water vapor from that packet, the general packet, the conditions are going to be different. Now let us consider the first condition wherein I add the wet adiabatic, wherein I add water vapor into the packet of air, and this is called as the wet adiabatic lapse rate. Okay, we know that when say a simple condition that I spoke about in an earlier lecture is that when we are thirsty and when we are given water, obviously we are going to drink it faster as compared to when we are not that thirsty and still we may be drinking water. You'll see that the conditions are going to be different. In that case, what happens is, as far as the wet adiabatic lapse rate is concerned, the moment you add some water vapor into an existing air packet as such, the rate at which the lapse rate or the temperature may fall is going to be much lesser than the normal lapse rate as such, because in the normal conditions it is 6.5. You'll see that in wet conditions it is going to be lower than that. It is going to be lower than that. Exactly opposite to that, you'll see that in drier, say adiabatic lapse rate, what happens is that the rate at which the temperatures may change in a packet of dry air are going to be much higher than the normal as such. And it is these things that are going to lead to these three conditions that we have in front of us: absolute stability, conditional stability, and absolute instability as such. Now, what do these three things mean? Okay, these are based on the first three observations that you are seeing up: adiabatic lapse rate, wet adiabatic lapse rate, and dry adiabatic lapse rate as such. Uh, Absolute stability. Okay, here you'll see that the absolute lapse rate, the adiabatic lapse rate is lower than the wet adiabatic lapse rate, which is obviously lower than the dry adiabatic lapse rate. Now, see what were the normal conditions: 6.5, 4, and 10. Okay, 6.5, 4, and 10. Now, what was 4? 4 was wet adiabatic lapse rate. Then 6.5 was adiabatic lapse rate, and 10 was dry adiabatic lapse rate. Now you'll see that normally this is the condition that 4 is less than 6.5 and 6.5 is less than 10. Now what happens is when these things exchange their positions, in the first condition what has happened, you will see that adiabatic lapse rate goes lesser than the wet adiabatic lapse rate as such. So these are going to be very different conditions as such, and which obviously is less than the dry adiabatic lapse rate as such. Conditional stability. Conditional stability. We are going to come to these terms and we are going to discuss this in detail, but try to understand the three conditions and the normal condition. This is what the normal condition is supposed to be. Absolute stability, okay, is going to be where your environmental lapse rate or adiabatic lapse rate is going to be lesser than a wet adiabatic lapse rate. That means it's going to be very much saturated as such. On the other hand, conditional stability is going to be where this moves to the center of these. That means this condition. Okay, the normal condition that we are referring to is conditional stability. Okay, you can see the upper square and this, they do match to each other. Then you have absolute instability when you're going to have heavy rains, where you will see that the wet adiabatic lapse rate is lesser than dry adiabatic lapse rate. And of course, you'll see that the environmental lapse rate is much higher than that. Means this is going to be a very hot day as such, and that leads to an absolute instability, and that is why you'll see you're going to have torrential convectional rainfall towards the latter part of the day. And that is how these three are related. We are going we are going to understand the diagrammatic aspect of all these three, how they are related to each other. But then let us now go into these things. Okay, what exactly happens in these conditions? That means whenever an unsaturated, okay, unsaturated parcel of air, sorry, so this is not the one. So yeah, you'll see that this is an unsaturated parcel of air is lifted. When it lifted, when it lifts itself, obviously the pressure is going to decrease. The pressure, it decreases. And because the pressure decreases, what happens is this is going to cool down. Okay, so this has cooled down from, okay, you'll see that from 32 to 22. That means there is a fall of 10 degrees centigrade. Got it? Okay, you'll see that it mentions here that it is cooling down at a rate of 10 degrees centigrade per 1,000 meters. On the other hand, what happens is when air is sinking down, you could say from here to here, from here to here, or from here to here. Okay, you'll see that while it climbs up, okay, the pressure is going to decrease. So obviously there is going to be a rise in the size of that particular air parcel, because of which it will cool down at dry adiabatic lapse rate. When it comes down, exactly opposite things happen. That's the pressure is going to increase. Now, because the pressure increases, obviously the sinking parcel, it is compressed. Because it is compressed, it warms up. You'll see that you can try this with your hand also. You'll see that when you close your fist and hold it so for some moments, not even minutes together, when you hold it, okay, you'll see that the pressure, you'll feel that it warms up as such. On the other hand, you'll see that when you want cooling, okay, what you do is you open your hand, and okay, so what you're doing is releasing pressure, and you are going to bring in pressure as such. So that is what happens when an unsaturated parcel of air is lifted, and it expands at a dry adiabatic lapse rate. Similarly, you'll see that when the rising air, okay, when the rising air expands, okay, you'll see that from here, let us say now in a condition where in the 32, it goes up, pressure is less, okay, this is dry adiabatic lapse rate. It goes down from 32 to 22, from 22 to 12, okay, at every moment you have 10 degrees, from 12 to 10. Now what happens is, okay, this rate is 10 degrees centigrade per 1,000 meters until air reaches dew point. Dew point is saturation. We have done this earlier. Okay, now when this reaches dew point, what happens there is air still continues to rise, but what has happened in this process? Okay, you'll see that this is dry adiabatic. At this level, this is the condensation level. Because of this, what has happened is that the vapor has condensed, and because of it now it has some amount of moisture in it, and because of that, you'll see that it translates into wet adiabatic lapse rate. So what was going up at a fall of 10 degrees now goes down below 6, that's 6.5, that is normal lapse rate, and it comes to 5 degrees, which is wet adiabatic lapse rate. So from 2 to -3. So 2, 1, 0, -1, -2, -3, 5. From 4,000 to 5,000 meters, it is still, you'll see there is condensation taking place. So wet adiabatic lapse rate. So what had started at 32 degrees at the surface, at 3,000 degrees went to 2, and from 2 to 3,000 to 5,000, next 2,000 meters, it has gone down to -8. Now this is a peculiar condition. As the air continues to rise, the latent heat released by condensation reduces the rate of cooling, right? Okay, the heat is there, okay, and that's why it reduces the rate of cooling. The wet adiabatic lapse rate is therefore always less than the dry adiabatic lapse rate. Now let us see what happens. In a stable atmosphere, okay, this is a stable atmosphere. When an unsaturated particle of air is lifted, okay, what is going to happen? Unsaturated. This is unsaturated, so fall is going to be 10 degrees. So 25 to 15, 15 to 5, 10 degrees at each level. Okay, because the temperature of the rising parcel is lower than the surrounding air. Now, why is this temperature lower? Because here you'll see that the environmental lapse rate, that's the normal lapse rate, is 5 degrees. So this also starts at 25, this also starts at 25. But at 1000 meters, this has cooled by 10 degrees. However, this has cooled by 5 degrees only. So there is a difference. There is a difference of 5 degrees here. And this is the rising air, that is this air, is cooler than the environment. Okay. Now, what happens is when this is further goes up, okay, this continues to go down in the environmental lapse rate. So from 20, it comes to 15. Now from this 15, it goes to 5. Now this is cooler, this side is cooler, and this side is warmer. Any cool substance is obviously going to be heavier. As a consequence, what is going to happen is that there is a tendency to come down. Because the temperature of the rising air parcel is lower than that of the surrounding environment, it will be heavier. And if allowed to do so, it will sink down to its original position. It will sink down to its original position. This is one condition. Now, what is absolute stability? Absolute stability. You will see that we have learned these terms here. Okay. We are doing this. What is the condition? That the adiabatic lapse rate is less than wet adiabatic lapse rate and dry adiabatic lapse rate as such. Okay, this is the condition which is called as absolute stability. Let us see what happens, and before that, let us see what are the conditions. The environmental lapse rate is here. This is 5 degrees. Okay, so the conditions are at the surface. Let me just shift this a bit. Yeah. So absolute stability, what does it say? Absolute stability prevails when the environmental lapse rate is less than the wet adiabatic lapse rate. The rising parcel of air is always cooler and heavier than the surrounding air. Okay, the rising parcel, म्हणजे हे आपण आधी जे पाहिलं, rising parcel is always cooler. Now we are seeing the same condition in a more explained diagram as such. The rising parcel, okay, what happens? The rising parcel is always cooler and heavier than the surrounding air. Surrounding air म्हणजे this absolute, environmental lapse rate, producing stability. okay, producing a type of stability as such. We'll come to this later. Okay, once we have understood what is actually happening as such. So start at both these start at 20 degrees. Because of some conditions, this starts rising. Okay, now what is this some condition? It may be obviously encountered with cold air. Okay, and it is pushed up the layer of cold air as such. While this is being pushed up, it may so happen that it may say it may get cooler. Okay, it may go cooler at a faster rate. While this is the normal thing which is happening, so this is from 10 to 15, sorry, 20 to 15, 5 degrees, 15 to 10, 5 degrees, 10 to 5, 5 degrees, 5 to 0, 5 degrees, and so on and so forth. On the other hand, see what is happening, particularly till this level, that this is cooling much faster. Okay, 10 to 10, 20 to 10, and 10 to 0 degrees as such. Okay, what happens is in the first 1,000 meters, rising air, this side is cooler by 5 degrees. By 2,000 meters, it gets cooler by 10 degrees as such. At this level, condensation starts happening. So that energy is utilized, and you'll see that it will then rise at a different level. Okay, so from 0, it's going to be -6. Okay, another -6 and another -6. But you'll see that continuously, may it be 10, may it be -6 or whatever. Okay, it is going to be cool. It is going to get cooler at a faster rate than this normal. So continuously, what happens is, see, rising air is 5 degrees cooler, 10 degrees cooler, 11 degrees cooler, 12 degrees cooler, 13 degrees cooler. So this is continuously going to be heavier, and because this is heavier, there is going to be a tendency to come down. There is going to be a tendency to come down as such. And because it is going to have a tendency to come down, this is called as stability. And whatever level it climbs up, it is always going to be cooler than the surrounding air. That is why you're going to call it as absolute stability. You're going to call it as absolute stability. So that is what absolute stability is, that at whatever height you see, the temperature of the rising air mass is going to be lesser than the normal temperature expected as far as the environmental lapse rate is concerned. Okay, now coming to the right side of your picture, let us now, let me clear this off. Okay, we come to this part, the B part of it. Okay, let us draw the temperature curves as such. You'll see that this environmental lapse rate curve is towards the right. And as far as this part is concerned, the curve is towards the left. Both of them have started till 2000 meters. What has happened is it is rising, but then it is faster. Okay, because it is 10 degrees per 1,000 meters. After this, it falls down to 6 degrees per 1,000 meter, and that's why you'll see that the curve is much gentler as compared to the red one. But whatever the cause, whatever the condition, both of them are always to the left of the environmental lapse rate. This is an easier way to remember. Okay, की environmental lapse rate ची कर्व कुठे आहे आणि त्याच्या अनुषंगाने रायझिंग एअर मासची कर्व कशी बिहेव करते, that is another way in which you can understand various types of conditions of stability as such. Okay, so whatever the condition, हे पुढच्या डायग्राम मध्ये अजून क्लिअर होईल, but remember here that whatever the condition, the rising air mass is cooling faster than the environmental lapse rate, and that is why it is called as absolute stability. Okay, that means whatever happens, the air mass tries to come down, the tendency is going to be there to come down as such. Okay, and in such conditions, what happens is you have very say fair. You'll see that in these both the photographs, you hardly see any clouds in front of you, and the conditions are very stable. And because of that, you'll see that the eagle is not even flapping its wings. It has just opened up its wings, and it is gliding on that air. It is gliding on that air. The same thing happens as far as hot air balloons are concerned. Areas which have a very regular weather condition like stability, absolute stability, are core areas where, say this hot air balloons, the game of hot air balloons is taken up as such. Okay, so this is what absolute stability means. Now, let us move to absolute instability. Now, going by this, आपण latest मगाचा डायग्राम केलाय, you'll see की तिकडे ही कर्व जी होती ऍब्सोल्यूट, तुमची एन्व्हायरमेंटल लॅप्स रेटची कर्व जी होती ही राईट साइडला होती, कंटिन्युअसली राईट साइडला होती. नाउ यू विल सी that this is continuously left side. Now, what does that mean that it is continuously left side? Let us first, the first thing you have to look here is this. What is the environmental lapse rate? The environmental lapse rate is 12 degrees. That means this is going to be a very hot day. This is going to be a very hot day. Okay. And what is happening here is that from 40, it is falling down. It is falling down to 28. So you'll see that this is 12 degrees from 28 to 16. Let us first look at these, because we have to look at this red part first. Now, this is going to go by its normal conditions. Okay, so what starts at 40 falls by 10 degrees and comes to 30, sorry. This 30 is higher than 28. So you'll see that this is to the right side of the curve of the environmental lapse rate. Then you go to 30, from 30 to 20 here. This has gone from 28 to 16 here. Okay, so the rising air initially was 2 degrees warmer. Now it is 4 degrees warmer. And in fact, now what is happening with this is this is going into condensation. And the moment it is going to go into condensation, okay, you'll see that wet adiabatic lapse rate is going to apply. And instead of now falling by 10 degrees, it is going to fall by 6 degrees. So from 20, it has come to 14. But what happens here? This side, what happens here? It still continues at the rate of wet adiabatic lapse rate after condensation. So from, this is this side. Now this continues at an environmental lapse rate of 12 degrees. So from 16, it goes down to 4. Another drop of 12, 12, 12. This was 10, 10, and now this is 6. So what happens is the rising air is warmer by 10. So you'll see that this gap is going to increase now. This gap is increased. Both started at the same level, but this gap is increasing. And your this curve stays to the right of your this curve. That's this curve. And it is because it is to the right that there is going to be instability. At whatever height you go, the rising air is always warmer, and that is why there is going to be a tendency to go up. What is the tendency? I'll just clear off. The tendency is to go up, and that is why unstable, and at whatever height it is always to the right, and that is why you call it absolute instability. Absolute instability as such. Cumulonimbus clouds will develop because of this, and you'll see that heights could vary from 4 kilometers to 5 kilometers, and you would be having heavy rains because of absolute instability as such. That was the second condition. You'll see. What was that second condition? Sorry, the third condition, that wet adiabatic lapse rate is lesser than dry adiabatic lapse rate, and this is your normal lapse rate, ALR. ALR. Okay. Now we go to the third condition, which is called as conditional instability. Now, when I say conditioned instability, okay, you'll see that this thing here, the relationship between the two curves is very intricate. They are not going much far away from each other. They are not at all going away from each other as such. And let us understand what exactly is happening with this whole issue at the base. Again, let us assume that this is going to be hot, basically because 40 degrees, 40 degrees. The environmental lapse rate, it is not as hot as it was earlier, but it is still it is hot. It is still hot. It is not as hot as this. Okay, here it was 12 degrees. Here it is 9 degrees as such. Hot, but not very, very hot. Okay, so in the normal conditions, when you climb 1,000 meters, okay, this will fall by 9 degrees, this will fall by 9 degrees. Okay, from here to here, another fall of 9 degrees. Okay, on the other hand, this fall is at 10 degrees. So from this will fall by 10 degrees to 30, and from this another 10 degrees. Now what happens here is the temperature of the rising air is 20 and the normal air is 22. Okay, normal air is 22. So this is going to be colder. Because of this colder, till this level, what is happening, the tendency is to come down. The tendency is to come down. Okay, now at 2000 meters, condensation takes place. Okay, you'll see what has happened here. Okay, there is a very small difference, very small difference. And as a consequence, you'll see that you can hardly see which way it is going. You can only understand by this diagram as such. After condensation, what is going to happen is the normal air is going to drop by 9 degrees. So from 22, it comes to 13, another 9 degrees. But because of condensation happened here, okay, you'll see that it will now rise by 6 degrees centigrade. Sorry, it will now fall by 6 degrees. So from 20 degrees, it will come down by 16 degrees to 14. Now what is the condition? That this becomes warmer. This becomes warmer by how many degrees? Just 1 degrees, but still it is warmer. So the tendency starts going up. You climb another 1,000 meters. This falls from 13 degrees to 4 degrees, another 9 degrees. But this is climbing by wet adiabatic lapse rate. So this will fall by 6 degrees. From 14, it will come down to 8 degrees. This is 4 degrees warmer because this is 4 degrees centigrade. This is 8 degrees centigrade. So this is going to be 8 minus 4. This is going to be warmer. So the tendency is going to go up. Okay. And here again, you'll see that it's going to further go up by another 1,000 meters. What has happened? Another 9. So from 4, it has gone down to minus 5. But from here, what actually happens is it has gone down by 6 degrees from 8 to 2. So there is a difference of air. The rising air gets to be 7 degrees warmer. Okay. Because of this condition here, things change. Initially, the tendency was going down. After a peculiar condition has taken place, it goes up from here. This is called as conditional instability. This is called as conditional instability as such. Okay, a condition has developed, and after that condition, because till here the tendency was to go down, but after that condition develops, instability comes up, and after which it starts rising. It starts rising as such. So this condition is called as conditional instability. So these are the 3 conditions in your syllabus that we are supposed to be doing. Okay, I would advise you all, what you should be doing is the fact that, sorry, I'll just clear this off. I'm going to give you an assignment on this, but at the basic level of understanding, हे जरा मोठ्या पानावर घ्यायचं तुम्ही, ग्राफ पेपरवर घ्यायचं, and start plotting these values. Okay, आणि एक पेन मध्ये घ्या, एक निळ्या शाई मध्ये घ्या, एक काळ्या शाई मध्ये घ्या, एक पेन्सिल मध्ये काढा. Okay, so you can come up with different combinations, and if you plot this, हे काढता काढता तुमच्या लक्षात येईल की असं आलंच पाहिजे. ऍक्च्युली नसेल आलं तर you'll see that as far as conditional instability is concerned, okay, where does it come from? Okay, you'll see that here it starts, because till here the tendency is going to go down, and from here the tendency is to go up as such. Okay, these are called as conditional stability, and this is of course stable, this is instable. Okay, they are going into opposite direction after a particular condition. that is condensation, and that is why this is called as conditional instability as such. Okay. Similarly, you can take a piece of paper on the same. You can plot absolute instability. This is the first two are relatively simpler. You'll see that this is your environmental lapse rate. This is your environmental lapse rate, and your whether it stays to the left of the environmental lapse rate curve of the rising air. On the other hand, here you'll see that it stays to the right, okay, whatever the condition, and that is why one is absolutely stable, one is absolutely unstable. लक्षात येते की ह्याला आपण ऍब्सोल्युटली स्टेबल का म्हणायचं, तर हे कंटिन्युअसली डाव्या हाताला आहे एन्व्हायरमेंटल लॅप्स रेटच्या, आणि ह्याला आपण ऍब्सोल्युटली इनस्टेबल का म्हणायचं, तर हे कंटिन्युअसली उजव्या हाताला आहे. आता डाव्या हाताला आणि उजव्या हाताला म्हणजे काय, तर दिस इज गोइंग टू बी वॉर्मर 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 वॉर्मर. उजव्या हाताला म्हणजे वॉर्मर वॉर्मर वॉर्मर, डाव्या हाताला म्हणजे कूलर 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 कूलर. ओके. And if the conditions are such that to some extent it goes up and the tendency is to come down, however, after a particular condition comes up, that's condensation here, okay, it tends to go up as such. Okay, and this is called as conditional instability. त्याच्या नावाने आपण थोडंसं याचं एक्सप्लेनेशन समजून घ्यायचा प्रयत्न करणार आहोत. त्याच्या नावाने आपण हे करून घ्यायचा प्रयत्न करणार आहोत. So this is what it is all about. Okay, this is something, say on a broader scale, what actually happened. This is an example of frontal rainfall, but you'll see that conditional instability is somewhat like this, that cold air is going to push it up, and we are going to come to this at some point of time when we are going to go into the polar front theory as such. So I'll just end it, and that was all for the various types of stability, instability, and conditional instability. Absolute stability, absolute instability, and conditional instability as such. I don't want to confuse you all, because the next time I've finished with the water vapor, the conditions, different conditions of water vapor, what happens with water vapor, why it happens is because of this absolute stability, absolute instability, and conditional uh, instability as such. Okay. And next time we're going to start with something else, and that's why I'm not going to go into the detail into those details today. So if you have any questions, or if you have any difficulties of having understood what we were doing today, I would still advise you all that the उजवीकडचा जो ग्राफ आहे, जर तुम्हाला कळलं नसेल, कळलं असेल तरी केलं तरी चांगलं आहे, की थोडीशी त्याची आपण म्हणतो ना की एक्स स्केल जी आहे ना, एक्स स्केल थोडीशी वाढवली. त्यांनी कसं केलंय, ते पुस्तकामध्ये बसवण्याकरता त्यांनी ते थोडंसं कॉम्प्रेस केलेलं आहे, बट स्टील यू कॅन अंडरस्टँड, कारण शेजारी एक ब्लॉक डायग्राम दिलेला आहे. तुम्ही जर स्वतः ती एक्स स्केल थोडीशी वाढवलीत, आणि इनफॅक्ट एक तुम्ही A4 साईजचा जर ग्राफ पेपर घेतला आणि त्याचे 4 भाग केले, त्या 4 भागामध्ये वेगवेगळ्या कंडिशन्स तुम्ही काढल्यात, तर एकाच ठिकाणी तुम्हाला त्याच्यामधला डिफरन्स काय आहे हा नेमका कळेल. In fact, I would like to give it as an assignment, and I would like you all to complete the assignment today itself, and I would like you all to post it on the group, not classroom. You post it on the group itself, so that let me see how well you have understood these things as such. Okay, each one of you all try, and you can use color pencils, you can use color pens, you can use pen and pencils, and a combination of all that, but see that you maintain the same theme through all the. असं व्हायला नको की तुम्ही एन्व्हायरमेंटल लॅप्स रेट एका डायग्राम मध्ये पेन मध्ये काढलाय, दुसऱ्या डायग्राम मध्ये तो पेन्सिल मध्ये काढलाय, तिसऱ्या डायग्राम मध्ये तुम्ही डॉटेड पेन काढलेला आहे, चौथ्या डायग्राम मध्ये तुम्ही ब्लॅक पेननी काढलेला आहे. ओके, सी कन्फ्युजन कधी होतं, वेन यू आर युझिंग अ डिफरंट थीम इन डिफरंट डायग्राम्स. इफ यू कीप एन्व्हायरमेंटल लॅप्स रेट साठी एक कलर तुम्ही ठरवला आणि तो चारही डायग्राम मध्ये, तिन्ही डायग्राम मध्ये तसाच ठेवला, ओके, देन विल सी की ड्राय एडियाबॅटिक लॅप्स रेट साठी तोच ठेवला, वेट एडियाबॅटिक लॅप्स रेट साठी तोच ठेवला. अंडरस्टँडिंग द डायग्राम that you have drawn will be much easier comparatively, and you would understand it better. Let me tell you that these diagrams are taken from Lutyens and Turbock, and of course, I'm going to post this explanation after some time in the link of this on our group. By then, you can just try, and if you have free time, I think you will have free time till 10:30. So you can just, I mean, it's not necessary that you take a graph paper. Okay, if you have the sense of scale, you can take a blank A4 sheet and you can draw it on that also. Don't run for a black, say, a graph paper, basically, because you have corona conditions here and there, and as a consequence, you should not land up in unfortunate trouble. So you can use, if you have graph paper, use graph paper. If you don't have graph paper, hardly matters. You can use a fresh A4 size clean paper as such. So that is it for today. I'll just take your attendance before I let you leave the meeting. Aishwarya Limaye, Asavari Kale, Prajakta Jadhav, Pratik Kokde, Pritam Ghosh, Revati Shinde, Rohit Gaikwad, Rohit Ithape, Rushikesh Aglave, Shreya Chavan, Sumit Nanavre, Tushar Kothore, Usha Wasave, Vandita Bhamre. Yes, one thing that I wanted to tell you all, ki some students have posted the next assignment as such. Yeah, before that, Tushar reminded me that the uh, point of insulation was covered in the earlier, that's the second assignment, and I've posted the same question. What I would like you all to do is you ignore temperature from that. Sorry, ignore insolation from that, and keep temperature and write your answer accordingly. Some students have already posted the assignment on of the third assignment, but let me tell you that I had told you all that you have to handwrite it. Two students, I don't remember the names now, but two students have posted it in a digital format. Please don't post it in a digital format. Post it in a handwritten format. And in some days from now, I will assess your second assignment. That's all from me. If you have any questions, I'm waiting for your questions. If you don't have